Hello everyone, this is Sando. Today I'm going to talk about how to implement batch normalization in deep learning. Since the batch normalization forward parsing is much complicated than the other layers I explained previously, so here I will use computational graph to help me to get a backward propagation for batch norm. If you like my videos, can support me by subscribing my channel and click the like of the videos. You can find the code for these videos in description below and all of my video list. Okay, so what and why is batch normalization? So batch normalization is taking a value of x over a mini batch, then trying to learn separate parameters alpha, gamma, and beta. Then what happening in batch normalization is we first take the mini batch mean and also calculate the mini batch variance. Then we use the mean and variance to normalize the value, and also we do the scale and shift the value to learn this gamma and beta to have the batch norm output. The big advantage of batch norm, it can tackle internal current shift in deep learning. At every epoch of training, we have small change in input distribution. This will be added up fast and amplified greatly deeper into the network. As a result, our neurons need to continue step to the change in input distribution, meaning that their learning capabilities are severely bottlenecked. So to solve these issues, we'll use batch norm. Batch norm also can be seen as a regulation method to prevent overfitting, because it multiplies each neuron by randomness, variance, and the samples. Those the randomness is the standardization of mini batch and also the mean. So as a result, each neuron has to learn to be robust to tackle this noise. Another small things it may helpful is for vanishing gradient. If you have checked my previous videos about the activation layers, I have mentioned there is a 10H functions has been used to use a activation function. Then its curve is like the picture here. Basically, you can tell that this front end and back end, the gradient of this curve is pretty flat, given the large or small input value. So the bench norm can basically normalize the values nearby the zero region so that we have a larger gradients, which is to prevent vanishing gradients problem. Now, so we already have the forward propagation. Then here is basically the cheating sheet for the whole backward propagations process. Eventually, we want to calculate the gradient of x, gradient of gamma, gradient of beta, given the gradient of output. So I'm going to teaching the step by step based on the 1, 2, 3 to the all the way to the 9. Then when I talk to each step, you can get back to this main picture to kind of understanding the big pictures. I don't own this graph because this is made by the author I mentioned below in his tech blog. All right, let's dive into this. So first, I'm going to talk the step 9 first. We have output. The dimension is the batch size multiplied the feature dimension. Then, using this computation graph operator, we want to get a gradient of this ND, which is the gamma x hat and the beta here. There's a few of rule for different operator in the computational graph. Then the first rule is for the plus operator. Basically, if we get the gradient of output, our gradient of input can be written as gradient of output multiply 1. So basically, you can think as take the derivative of this one, and for the betas, we take the derivative of this one. This one is coming here and multiply the gradient of output. Then we already have this gamma x hat. Then back to our step 8. Oh, I forgot mention one thing. For the gradient of output here as nd dimension, back to the gamma x hat, it's no problem because their dimension is same. But our beta here is the dimension of d, right? So what can we do to reduce from the nd to the d? Of course, just the sum of them from the 1 to n. Then eventually we will have the gradient of dimension d. Now let's go to step 8. We have nd here. Then we have an operator multiply. Then we will want to get a gradient of gamma and the x hat. So given the gamma multiply x hat equal to gamma x hat, we will use the second rule in the computation graph for the multiply operator. Basically, the gradient of one part will be equal to the value of second part multiply the gradient of output. The same thing for the gradient of gamma, we need to multiply the x hat. So this is the second rule for multiply operator. Same thing, like because our gamma dimension is d, we need to reduce from nd to d. So here we will apply a summation here from 1 to n. So next, for step 7, we have this gamma x, hat x at nd, another multiply operator. So now we know we use root 2. Basically use the second part value multiply the gradient output. Also, here the inverse variance we want to have is dimension of d. Then we will apply a summation from 1 to n here as well. For step 6, this is simple, just one input and one output. We can treat this as either multiply or plus operators, like plus 0, multiply 1, both works. So essentially just take a derivative of the representation here and multiply the gradient of output. Then we will get a gradient of input. Step 5, similar things. It's a simple one input and one output. And step 4 is a little bit tricky because previously we saw from the output of nd how to reduce to d, right? That's take the summation. Here we have a dimension d, then we want to expand it to n and d. So what we do here is we basically gradient of output multiply n by d matrix, then divide by n. So basically you can think we put the gradient into n parts and separately for each row of the gradient, because eventually we will have the 1 divided by n here. Other than that, I think it's all simple things. But here I just denote it as rule 3. Step 3 is simple. One thing I want to mention is here. So it mentions x mil. Actually, it's x minus mil. But this is for simple mark. We will have a x mil 1 previously. So just to make this distinguishable. Then why we have x mil 1 and x mil 2? This is explained in the step 2. That's because we have two output. Then here is also a plus operator. Even if it's minus, you can just think about the multiply and minus to the second part. So it becomes x plus minus mu. I call this is root 4 because we have two output. The equation also will be different. The difference is that for the user plus operator is 1, always multiply the gradient of output, right? But right now we have two output, so multiply gradient output become the plus of two gradients output. Same thing for the mu here. Mu we put it minus 1, so we put a minus 1 here, and we just multiply the gradient of these two output. One thing we need to also remember, like if output is nd and we have d, we need to add a summation here. Then finally, we come to the last two steps. For the step 1, we use a root 3 because it's from d expand to nd, right? Then for the final step, which is 0 step, we have two output here. We use root 4 basically to plus two gradient of output. All right, so now we have finished the whole backward propagations process to get the gradient of x, gradient of gamma, gradient of beta. Now let's see the code. One thing to mention in the forward propagation, one trick I do here is to get a flattened of input because the input may not necessarily to be n and d. For example, in the 2D convolution, we have d marked as dimension of weight multiplied dimension of height, then dimension of the features. Then d here basically is the multiplication of those three dimensions. We calculate the sample mean and the sample variance here. Then x hat, eventually get the output. One thing to note here is like this is only applied in the training mode. Then if we have to do this in the testing mode, it's not make sense to only use the sample means variance in one single mini batch, right? So we want to use the whole data set mini batch. So here we will calculate the running mean and the variance and save in the cache. We also don't want the running mean, running variance only be current mini batch mean and variance. So this is why we multiply our momentum here to fusion the previous mean and the current mean. So you can check more details here in the comments here. In the testing, we don't calculate the sample mean and sample variance. We directly use the running mean and the running variance in our cache. Backward propagation is not much to explain. You can find the equation here. Probably I'm using in different equations compared with the previous step-by-step equation. That's because I'm using more compact end-to-end version to represent each variable. You can find those end-to-end equations online. I'm not going too much details for this. But I believe if you understand the step-by-step equation, that's good enough for you to understand how to get the backward propagation equation right for the batch normalization. All right, so that's all I want to talk today. Hopefully you enjoyed these videos. Then see you in the next video.